Hello, and welcome to the Lightwave Logic presentation that was given to the Sidoti Financial Conference in New York City on January 10th, 2011. My name is Phil Smith, and I'm the chairman of Lightwave Logic. As you know, we are listed on the over-the-counter bulletin board, and our trading symbol is LWLG. Lightwave has, in fact, a very exciting disruptive technology, which is our material platform. We're going to try and discuss that in some detail throughout this presentation. Hopefully at the end you'll have a better understanding of what I mean. To start off with, to keep the lawyers happy and the SEC happy, we have to put the safe harbor statement in because we will be using forward statements here, which can in fact, no one can guarantee the future or predict the future with accuracy. We're giving you our best shot, and if you'll take to heart this statement, you'll understand what I mean. Now, today in the agenda, we're going to discuss, first of all, the electro-optic polymer. What is it? A lot of people throw that term around, but I'm not sure a lot of us really understand what it means. And then I'm going to talk about the breakthrough that we've had, why our polymer is different than, or why our electro-optic polymer is different than others that have been out there for quite a while. We have very strong intellectual property. I'm going to discuss that in some detail. We have a vision for where we are today and where we're going. The chip market is one of the first markets we've addressed. I'm going to put some data up and some actual numbers. The holy grail of optics may in fact be the thing we found with third order. I'm going to talk about that. The vertical trajectory of this business will not take off like a traditional startup because a lot of big companies will be using this material. The best way to think about electro-optic polymer, it has the opportunity within the microelectronics marketplace to replace copper. It can be used almost every place copper can be used. It's cheaper, faster, uses less power, which means it generates less heat, and it can be put into a flexible form factor. And finally, I'm going to discuss the management team that will take us to these opportunities and successfully accomplish the goals we've set for the company. Okay, the first thing we're going to talk about is the electro-optic polymer. What is it? Well, basically, all it is a piece of plastic or glass with unique properties. We can put our material on top of it, and our material kind of makes a pathway for light, much like a fiber optic cable does, but it's at the molecular level. And what it does, it allows light to pass through our chromophores, which are basically dyes, which is a fancy term for prism. You can think of prism as at the molecular level, letting certain frequencies of light through at the speed of light. Now, why do people want this? Well, first of all, it's faster because it operates at the speed of light. Secondly, it takes much less power. I'm going to give you an actual example on what the savings of that is for manufacturers. It's cheaper. And finally, it has a very flexible form factor. So these are all attributes which make electro-optic polymers very interesting. But they have not gotten through till today. Why haven't they been used? Well, the breakthrough that we're going to discuss points out the things that most people have been unable to achieve. In fact, no one has achieved this with electro-optic polymers that we're aware of other than Lightwave as of today. The first thing in the breakthrough that we're going to discuss is temperature stability. You have to, in the manufacturing, chip manufacturing and wave solder process manufacturing, be able to withstand temperatures of 270 to 320 degrees C. That means that these polymers have to stay together. They can't be disrupted because of the temperature. If they did, then they'd change the characteristics and they would become useless. This has been a big issue for most of the people in the polymer business. The second thing, and we do have thermal stability. That's been proven and verified by third parties. The second thing is photochemical stability, and this graphic doesn't do it much good, but what it says is when you hit these chromophores, these prisms, billions of times a second with a laser, will they bleach out? Will they change the frequency? Will they change the chemical makeup? And we, in fact, have tested ours at 72 hours with a very high-intensity laser and not been able to see any significant or any degradation of the dye itself or of the chromophore. And the final thing is poling. You've got to have stable poling. Poling is basically when you put an electric charge on the material and line all the molecules up, and they stay that way for a long period of time. It's a one-time process. The best example I can give you is shown in this picture. This is actually an opaque window in Taser International where I have some connections. And basically when you put the power on, the window goes clear. It's the same thing with poling. When we set our molecules up with this electric charge, it allows light to pass through, and again, you only have to do it once. Here's another example of another part of the window. Again, the power on, the power off. Here it is again. power on, power off, and finally the power on, power off. This has real applications down the road for things called optical limiters, and I'll specifically cover that later in the presentation. But polling is important, and you have to be able to poll your material once and keep it that way. We've had some material polled for 3 years with no problems, and therefore this is something that our competitors have had difficulty doing, and the reason is this material is inside microprocessor chips, as an example, and they can't be taking those chips apart to repoll the material at some time in the future. So these 3 issues of stability, thermal, photochemical, and polling, are really, in essence, why our material will be successful in this marketplace. The next thing we're going to talk about is strong intellectual property. Today we have 6 patent applications covering composition of matter. Composition of matter, by the way, is the most basic patent form you can get, and once it's protected, it's very, very well protected. We've had 2 patents allowed in November, one for our chromophore, which is our dye and our prisms, and the other for a spacer. And the spacer system is what keeps the molecules lined up the same way. Think of a railroad tie between 2 rails. That's what spacers are for, and those 2 have been allowed. We have 4 more that have been applied for, and I'm told that there's 31 patent applications internationally currently in process. But with these 2 allowed patents, it really does protect our material platform and gives us good, strong patent protection going forward, which will be important. As a material company, we're going to be doing a licensing and royalty model down the road, and good, strong intellectual property is important in those negotiations. Finally, our vision. Let's talk about our vision. The 20th century we saw, and actually the first part of this century, as the one of electrons. You know, the transistor was developed, and there were great advances made in the computer business. You're all well aware of them using silicon. We really see this decade as the decade of the photons. This diagram here is actually a hybrid chip. It came from IBM, and they recently announced using the same chip. Let me explain. The bottom layer is a process layer, and the middle one is a memory layer, both using silicon, and then the top one uses electro-optical properties. They have used silicon with photonics and silicon photonics, and we use polymer-based photonics, and I'll talk about that. The advantage we have in this particular application, or any application, is we're cheaper and we're faster than using silicon with photonics on silicon. So with this capability, it will eventually lead to a plastic chip, and all plastic chip leads to an all optical computer, which factually has never been obtained to this date. Now let's talk about within chip communication, within the chip itself. We've got a basic microprocessor chip here, and you'll see why in a minute. And the basic CPU layer is silicon. The next layer is silicon using memory. And the final one is using our material. Now, why would people want to use our material and make this a hybrid chip? Well, let's take a look at a typical microprocessor chip. A typical one today generates or consumes about 90 to 130 watts of power. So what you have is these. On the left, you see the cooktop, what's referred to as the cooktop. In the middle, you see all the fins trying to keep the processor cool. And on the right, you see an actual fan attached to it to keep it cool. With our material, we can reduce power by 70%. We can take that 90 to 130 watts down to 27 to 39 watts. Why is that important? Well, first of all, it generates a lot less heat, which if you talk to people, is one of the real design problems in enclosed spaces like smartphones, laptops, etc. So less heat is a big issue for design engineers. And importantly for us is longer battery life for these things. I mean, we all know what it's like to be charging our battery more often. So these are 2 key issues for the microprocessor industry. And again, remember, we're cheaper, we're faster, flexible form factor, and now we consume less power, which is really an important issue in the industry. Let's talk about the chip market. It was one of the first markets we really went and looked at and addressed. And here's some information from International Data Corp, which is the sources listed at the bottom left-hand side. As you can see, the chip market is about $270 billion worldwide last year, growing to about $350, growing about 9% a year. Now, what's significant in this is that 40% of the total chip market is computer chips. So if you look at 2010, last year, it's a little over $100 billion just to computer chips. And again, that's dominated by 2 suppliers. Again, this is IDC information. Intel owns about 80 to 82% of the market, and AMD owns about 16% of the market. So you have 2 suppliers that pretty well dominate this market, and they both have an interest, no doubt, in using our types of material, or should have an interest in using our material to reduce the heat and the power for the other reasons I've stated. Now, if you look at the unit growth, it's even faster. It's about 15%. We're growing from about 350 million units a year to about 700 million units a year. And once implemented, this material would be used across the entire product line. In my humble estimation, this is about a 3-year, maximum 5-year, till they have it completely integrated in their total product line, because they generate about that many new products over a 3 to 5-year horizon. So you can take a look at that $100 billion market opportunity there in 2010, and on a royalty basis, you can put whatever royalty number you want on it, but just mathematically speaking, a 1% royalty, we're not saying we'd get that, but a 1% royalty would represent $1 billion. And that's why I talk about a vertical trajectory on this business. Once it goes, it's going to be driven by the big companies using this material, not by us. We can supply the material, or they can supply it under license, and it'll go according to their speed, not ours. And that's why the growth will be very rapid once we get this accepted and used by these suppliers. The next market would be the inter-chip communications. This is between chips on a printed circuit board, shown here. And if you take them off and look at the board itself, there's a lot of copper tracings on there. Those can all be replaced using photo etching using our material. Again, it's cheaper, it's faster, it operates at the speed of light, and it can be built into a flexible form factor. This market, according to IDC, is about a $70 billion market in the worldwide.